Hi everyone, this is Mrs. J, and today we're going to be calculating limits using the limit laws. Alright, I have a quick warm-up for you guys, so please pause the video and give it a try. Alright, go ahead and check your work here. So here you can see a graph of sine of x over x. It is undefined when x equals 0, but you can see that it is clearly approaching 1 from the left and the right, so that's our limit. And for 1 minus cosine of x over x, it is clearly approaching 0 from left and right, so that will be our limit. Now these are two special trigonometric limits, and for now I'm going to say that these are important enough where you should just memorize them. Later on we'll learn other ways that we can find them, but these two limits, you should try to commit these to your memory now. Alright, so before we start talking about what are called our limit laws, I want to just talk about a couple common notation errors that we see with limits. So first, the correct way to evaluate a limit. Here's our original limit. Anytime we're doing anything within the limit, such as simplifying, we should still have the limit as x approaches whatever value out front. If we're simplifying, again, look here, we still have the limit as x approaches 3, and then as you actually start to find the limit, then the word limit can disappear, and your final answer should just be a value. So a first really common error we see is that the limit disappears altogether. So in the process of simplifying the function, before we're actually finding the limit, sometimes people forget to write the word limit. So don't forget, we need to write the word limit every time until we actually start the process of finding the limit. Another common error that we see is what's called an empty limit. So you're just going to have, we'll see that we just have the word limit, but we're not stating what we're finding the limit of, so don't let your work disappear along the way. We also commonly see a limit to nowhere, so we forget the x approaches whatever value on the bottom. So just try not to, don't get lazy. You do need to write it out in every single step. And then the last thing to watch out for, this is actually a problem with how you write your final answer. Again, when you're finding a limit, your final answer should just be a value. And it's really common for us to actually see that people write the word limit with what x is approaching as part of the answer. But again, once we've actually found what the limit is, our answer should just be that value. All right, so now let's take a look at our limit laws. I know it looks like a lot, but really they're pretty intuitive, so it's not necessarily things that you need to memorize as long as you understand them. So first, we are defining c as a constant. The limit as x approaches a of f of x is L, and the limit as x approaches a of g of x is m. So first, the sum or difference laws. This states that the limit of a sum or difference can actually be found by taking the sum or difference of the individual limit. So here you'll see that we have the limit of f of x plus g of x. So we actually take the individual limits and you can add them up or subtract them depending on whether you have a sum or a difference. The constant multiple law says that the limit of a constant times a function can be found by simply doing the constant times the limit of the function. So you'll see that it's just L times C. So we can essentially kind of pull that constant out and find the limit of the remaining function. The product law and the quotient law are very similar. The limit of a product is simply the product of the limits. So here you can see it's L times M. And here the limit of a quotient is the quotient of the limits. So you're taking the limit of this quotient. You can find the individual limits and take the quotient, the limit of those, the quotient of those. So here you do just need to make sure that m does not equal 0, so your limit is not undefined. The power law states that if you are finding the limit of a function raised to the power, you can simply raise that the limit of the function to that power. You're essentially using the product law up here repeatedly. So it's essentially the product law with multiple products, more than one power of your function. The root law says that if you are taking the limit of the nth root of a function, you could actually take the nth root of the limit of that function. So it's simply the nth root of L, which is the limit of f of x. Here we are assuming that n is a positive integer, and if n is even, of course, L should be greater than or equal to 0. Next we have the composite law, which says if you're taking the limit of a composite, like f of g of x, we can actually find f of the limit of g of x. So just to make it a little bit easier to find that limit, the log law states that if you are taking the limit of the natural log of a function, we can actually take the natural log of the limit of that function. So you'll see that the result is the natural log of L, which was the limit of f of x. And last, a couple special limits. This is called a constant limit. So the limit as x approaches a of c, remember c is just a constant, will just always equal c. Here, this is called an identity limit. The limit as x approaches a of x will equal just simply a. And then here, we have the limit as x approaches a of x to the power of n equals a to the power of n. So you can see in these two, we're essentially just doing direct substitution, and same with this one right here. The limit as x approaches a of the nth root of x will just be the nth root of a. So just direct substitution, of course, assuming that n is a positive integer here and n is even. And if n is even, we're assuming that a is greater than 0 within our radicand. So again, these are our limit laws, and you're going to see we can use these again to help us evaluate our limits algebraically. All right, so when we are finding a limit algebraically, we're essentially going to try direct substitution every time, and that's essentially putting our limit laws to use. Now, if we try a direct substitution and we get a real number, that is our answer, and we are done. However, sometimes we'll get what's called an indeterminate form. So one indeterminate form would be the form of 0 over 0. So if you plug in the value for your that x is approaching and you get 0 over 0, again, this is the indeterminate form, and our goal will be to manipulate our function until it no longer gives us this indeterminate form. So you can do that sometimes by factoring or simplifying or even rationalizing. So sometimes we'll actually even be rationalizing the numerator to help us with this. So we're essentially looking for any way that we can rewrite our function, and then we should be able to use direct substitution from there to obtain our limit. Another thing that we might see is what's called the undefined form. So if we have a number over 0 that's undefined at that value, which means we will have a vertical asymptote. So from here, what we're going to need to do is we're going to need to perform some sign analysis to determine the behavior on either side of our asymptote, and that will allow us to determine if the asymptote exists, or if the limit exists, if the behavior matches, or maybe if the limit does not exist, if the behavior does not match. So these are really the three cases that we'll be working with today. All right, let's try these first two examples together. So we're going to find the limits if they exist. So remember we said to evaluate the limit, we're going to always try doing direct substitution first. So to find the limit as x approaches 2, we're really just going to substitute 2 into our function. So we have 4 plus 4 plus 4 all over 4. So that gives us a limit of 3. And since it is a real number, that is in fact our limit. Okay, if we look at our next one, we're finding the limit as x approaches c of this polynomial. So we are just going to substitute. So we actually get c cubed plus 4c squared minus 3. This is, it's not an undefined number, and this actually will be our limit. I know it looks a little bit strange because it has the variable c in it, but as long as it's not, an undefined or imaginary number, it will work for our limit. All right, so I have one for you to try on your own. Go ahead and pause the video and give it a shot. All right, go ahead and check your work here. You can see we can use direct substitution to find the limit of -9. All right, let's try another couple examples together. So here we're finding the limit as x approaches 1 of this function. So if you do direct substitution here, so we have 1 minus 3 plus 2 over 1 minus 1, we actually get 0 over 0. So this is that indeterminate form that we were talking about. And when we see this indeterminate form, it means that we're going to want to look back at this function and see if we can manipulate it so it no longer gives us that 0 over 0. So one thing we can always try with something like this is we can actually factor our function. So notice I still have my limit symbol and what it's approaching. In my numerator, we can factor that. It's x minus 2 times x minus 1. And then here, x plus 1 times x minus 1. So we can factor and we can actually simplify, and we're left with the limit as x approaches 1 of x minus 2 over x plus 1. So now if we try direct substitution from here, we got 1 minus 2 over 1 plus 1. So we actually get negative 1/2. So from here, we were able to obtain a real number. So this is our answer. So you can see we did have to do a little extra work to manipulate what our function looks like, but then from there we were just able to use direct substitution. Okay, let's look at the next example over here. So again, let's try our direct substitution and see what happens. So it gives us 1 over 2 plus 0 minus 1 over 2 over 0. So we get 0 over 0, so again, we get that indeterminate form. So we're going to try to see if there's a way we can rewrite our function so we no longer see that. So one thing we can try doing is we can try combining the fractions in our numerator. So we're going to want to create a common denominator here. So I'm going to multiply this by 2 over 2, and I'm going to multiply this by 2 plus x over 2 plus x. And that gives us the limit of 2 minus 2 plus x over 2x times 2 plus x. So this is the denominator of our numerator, and this will jump right to the denominator as well. So if we continue simplifying, we get negative x over 2x times 2 plus x. And so we have the limit as x approaches 0 of negative 1 over 2 times 2 plus x. So we've simplified our function. So now let's see if we can evaluate this limit using direct substitution. So this gives us negative 1 over 2 times 2 plus 0. So we do get the limit of negative 1/4. All right, let's try another one together. So here we have the limit as x approaches 0 of this function. So we'll always start by, again, trying that direct substitution. So we get square root of 1 minus 1 all over 0. So we get 0 over 0, so indeterminate. So again, we need to find some way to manipulate our function. And in this case, since we have that radical, one thing we can try is rationalizing. And I know in the past we've only rationalized the denominator just to make sure there's no radical in our denominator, but sometimes with functions like these, it could be useful to rationalize the numerator. So let's give that a try. So we're going to actually multiply the numerator and denominator by our conjugate, which would be square root of 1 plus x plus 1. And when we do this, again, multiplying by the conjugate should clear your radical. So when I do this square root times this square root, it just becomes 1 plus x. And then the next two steps of FOIL would cancel out, and then we're just left with minus 1. And then in the denominator, we have x times the square root of 1 plus x plus 1. And let's see if we can simplify a little bit more before we try direct substitution again. Here you can see that the ones cancel out. And then we have x over x, which is a factor in the denominator. So those will also cancel out, or they'll reduce to 1. So it's 1 over square root of 1 plus x plus 1. So let's see if we can find this limit using direct substitution. So it's 1 over the square root of 1 plus 1, which does give us a real number of 1 over 2. All right, so I've got a couple for you to try on your own, so please pause the video and give them a shot. All right, go ahead and check. So for both of these, plugging in using direct substitution gives us that indeterminate form. So for the first one, we can factor our function, which allows us to simplify to this, and then we can use direct substitution from here. And then for our second one, we can multiply the numerator and denominator by our conjugate, which gives us this, which again simplifies to something that we can finish finding the limit using direct substitution. So you should get 3/2 and -1/2. All right, so let's try another one together. So here, let's try doing direct substitution to evaluate this limit. So when I do that, we get 2/0 because this factor of x squared doesn't matter what this factor is, it's multiplied by 0. So here we get undefined, which means that we have a vertical asymptote. So that means that we need to do a little bit of sign analysis to see what's happening as x approaches from the left and as x approaches from the right to determine if a limit exists. So again, we actually have two vertical asymptotes here. We have a vertical asymptote at x equals 0 and at x equals 3, but we're just trying to determine the limit as x approaches 0. So we are going to have to find the left and the right hand limit around x equals 0. So let's start with the limit as x approaches 0 from the left of our function, x plus 2 over x squared times x minus 3. So imagine some value that's just a little bit less than 0. So let's imagine that we're substituting -0.001. So that's our value. And again, we just want to know what the sign of each factor is. So if we plug in -0.001 and we add 2, the factor in the numerator is positive. X squared, this factor, when we square it, will always remain positive. And then x minus 3, if we use this x value, it is negative. So if you look at the signs, positive divided by a positive times a negative gives us negative. So on the left side, it will approach -infinity. Now let's see as x approaches 0 from the right. So again, we're just picking a number that is slightly larger than 0, like 0.001. And notice it's the positive version this time. So the factor in our numerator will be positive. The x squared will always be positive. And then this 0.001 minus 3 will be negative. So again, this gives us -infinity. So since the behavior on the left side of our asymptote matches the behavior on our right, we can actually say that this limit exists. So the limit as x approaches 0 of that function is -infinity. And if you ever have a case where you look at the left and the right hand limits and they are not the same, we would say that the limit does not exist, which is very possible for these types of problems. All right, so go ahead and pause the video and give this one a try on your own. All right, so you can see here on that since we have the undefined answer with direct substitution, I found the limit as x approaches 2 from the left and the limit as x approaches 2 from the right. These are the values that I was kind of using to do my sign analysis. And what I found was that the limit as x approaches 2 from the left was -infinity, but from the right it was positive infinity. So that means that the overall limit does not exist. All right, so now we're going to try one where we're finding the limit of an absolute value function. So again, if you plug in, if you use direct substitution to try to find this limit, you end up with 0/0, so you get that indeterminate form. So we're going to need to try to find a way to manipulate this function. And we can actually rewrite any absolute value function as a piecewise function. So we can have two different functions, and we can actually evaluate the left and the right side limits to see if a limit exists. So just a quick reminder, the function absolute value of x can be written as a piecewise function. The function to the right of 0 is just x, so that's x for x is greater than or equal to 0. And then it's the opposite of whatever is in our absolute value sign for everything to the left of 0. And remember, this just makes kind of that V-shaped graph like this. So again, this is our parent function. So essentially to the right and left of our vertex, we simply have linear functions that are opposites. So the first thing I'm going to do is I'm actually going to rewrite our function here as a piecewise function. So this function, so this part, the absolute value part here, this has a vertex at +2 because this is just shifted to the right 2. So it kind of looks something like this. So again, it's just been shifted to the right 2. For everything to the right of our vertex, our function is essentially the same except without the absolute value signs. So that's for everything greater than 2, which again is where our vertex is. But then everything for whenever x is less than 2, so to the left of our vertex, our absolute value portion is going to be opposite. So we essentially just multiply it by -1. So notice I have the negative with the parentheses, so I'm multiplying the entire thing by -1. So here we have our piecewise function. I'm going to make this a little bigger. So it looks like this. So when we're evaluating the left and the right hand limits, we can use the two different parts of our piecewise function. So to find the limit as x approaches 2 from the right, we're going to use this portion because this describes everything to the right of 2. So we'll use the function x minus 2 over x squared minus 4, and we could do direct substitution there. So we have 2 minus 2 over 4 minus 4. So we still get the indeterminate form, which is fine. So let's look at our function and see if there's a way we can maybe simplify it. I see that we can factor the denominator. So we have x minus 2 times x minus 2 times x plus 2. So we're really finding the limit as x approaches 2 from the right of 1 over x plus 2, cancel out those common factors. And now we can try direct substitution again. 1 over 2 plus 2 equals 1 over 4. So that's our right-hand limit. And now for our left-hand limit, we're going to need to use this portion of our piecewise function. So the limit as x approaches 2 from the left of negative x minus 2 over x plus 2 times x minus 2. So the limit as x approaches 2 from the left of -1 over x plus 2. And so now we can do our direct substitution, -1 over 2 plus 2. So we get -1/4. So we can see that the left hand and the right hand limits are not the same, which means that we can conclude that the limit as x approaches 2 of the absolute value of x minus 2 over x squared minus 4 does not exist. So that is our final answer. All right, so again, go ahead and pause the video and give this one a try on your own. Okay, go ahead and check your work here. So you can see that I rewrote this as a piecewise function because if we use direct substitution, we get 0 over 0, so we have the indeterminate. So to the right of 0, we can use the function x over x, and to the left of 0, it would be the function negative x over x. So for both of those, if we do the right hand and left hand limits, we'll simplify and we essentially have the constant limit. So the limit from the right is equal to 1, but the limit from the left is equal to -1. So again, this overall limit does not exist. All right, the last thing we're going to talk about is what's called the squeeze theorem, which we can use to help us find some kind of trickier limits. So here we're stating that f of x is less than or equal to g of x, which is less than or equal to h of x when x is near a, except possibly at a. And it is also given that the limit as x approaches a of f of x equals the limit as x approaches a of h of x, which equals, we'll say L. So notice the limits of your two outer functions is the same as x approaches a. So if this is true, then we can state, using the squeeze theorem, that the limit as x approaches a of g of x also equals L. So here's kind of a graphical representation of what's happening. So here's our three functions. So notice that as we're getting close to a, f of x is always less than g of x, which is also always less than h of x. And again, this is when we only really care that that's happening when we're close to a. If you look way over here, there is a time when g of x is greater than f of x or h of x, but really as long as this statement is true when you're close to the value you're approaching, then we can use squeeze theorem. So if the limit, again, of your top function is equal to the limit of your bottom function, then that means that the limit of the one that's squeezed in between must also equal L, or whatever that value is. All right, let's give this one a try together. So here we're going to try to prove that the limit as x approaches 0 of x squared times the cosine of 1 over x equals 0, and we're going to use the squeeze theorem to do so. So first, we're going to have to find a way to find a function that is always less than this function and always greater than this function as we approach 0. So first, I'm going to start with just the trig part of our function. So if you go way back in your brain and you pull out your knowledge of trig functions, you'll hopefully remember that the range, or the output, of your cosine function is always between and including -1 and +1. So we know that any of these values we can say are going to be greater than or equal to -1, and they're going to be less than or equal to +1. And again, this is just a fact about the range of cosine. But now this is the function we want to achieve. So we want to have that multiplied by x squared. So we can actually just multiply every part of our inequality by x squared. And we can do this because since our x value is being squared, we know that the result is always positive. So we don't have to worry about, maybe having to flip our inequality signs. And then again, it's totally legal as long as we're multiplying all three parts of our inequality by that same value. So now it's like we have three different functions. So we have our h of x. I'll call this h of x. It doesn't really matter what we call this. Here's g of x. And here's, let's say, f of x. So when we are approaching 0, we know that this function is always greater than this function, which we're trying to find the limit of, which is always greater than this function. So we can try to use the squeeze theorem. So first we're going to find the limit as x approaches 0 of h of x. And we can do that with direct substitution. We plug it right in here and we get 0. And then we need to find the limit as x approaches 0 of f of x, which is just x squared, which is also 0 using direct substitution. So since the limit of our two outer functions as x approaches 0 is the same, we can conclude, we can say, therefore, the limit as x approaches 0 of x squared times the cosine of 1 over x also equals 0. And we could show that by using the squeeze theorem. And really quick, I'd like to show you just a picture of what these three graphs look like because it's kind of interesting. All right, so here's a picture of our graph. So here's positive x squared, here's negative x squared, and here's that x squared times cosine of 1 over x. So you can see as x approaches 0, this function is always greater than our trig function, which is always greater than our negative quadratic function. And again, you can see we are approaching 0. All of these x values are really, really, really tiny. So just kind of an interesting looking graph that I wanted to show you guys. All right, here is the last problem for you to try on your own. So again, pause the video and hit play when you're ready to check. All right, so go ahead and check your work. Since this inequality is given to us when we are close to x equals 1, so between 0 and 2, which again is really all we care about, then if we find that the limit as x approaches 1 of 3x is equal to limit as x approaches 1 of x cubed plus 2, and they are the same, they're each equal to 3, then we can show that that is also the limit as x approaches 1 of f of x. So it is also equal to 3, and we can justify that with the squeeze theorem. All right, so that is all for today's video. Thank you so much for watching.